the fundamental theorem of calculus has two parts. We mentioned part 2 last time. And part 2 is mainly used to evaluate the definite integrals. Okay. Now let's recall, to evaluate the definite integral of a function from a to b, the answer is a number, right? All we need is to get a particular antiderivative. We use uppercase F, the big F, to denote a particular antiderivative of the integrand. And then you evaluate the antiderivative at the upper limit of b, and evaluate the antiderivative at the lower limit of a, and then you subtract the two values of the antiderivative. A symbolic notation is that notation. So this means the difference between two values of the antiderivative. Okay. This is mainly used to evaluate the integrals. Okay. Actually, theoretically, part 1 is kind of more important. So because if you actually want to prove part 2, you need to use part 1. Okay, now we are going to talk about part 1. The first thing we do is to try to understand the meaning of part 1. Okay. The second thing we do is try to use the physical meaning to see why both part 1 and part 2 are true. Okay, now let's talk about the meaning first. Okay, the meaning. Okay. Some people call this function the upper limit function. Okay, the upper limit function. So before we talk about the upper limit function, now let me. Before we talk about the upper limit function, now let me try to use a particular question to show you the meaning of the upper limit function. Okay. You'll try to remember the definition of upper limit function. Okay, so g of x is defined as from a to x. The integrand is a function of t. Okay. I will show you the definition. The function notation is denoted using g of x. Okay. Again, the first part of FTC is kind of more important. I'm telling you the meaning of the function g of x. So g of x is defined using the definite integral from the lower limit of a. You kind of fix the lower limit, and then you change the upper limit. Okay, and then for a given function, so now let's say f of x. So you are given a continuous function. So now let's say f of x. Now let's say f of x. The integrand now, for some reason, I'm going to use f of t to denote the integrand. In particular, I'm using t to denote the integration variable. Okay, if you have t here, the whole integral is going to be an integral of t. Okay, if the function is represented using f of t, and then the d part, you also write the d part using dt. Okay, I'm trying to say these two variables, these two locations always have the same variable. So maybe before we talk about this function, now let me try to tell you one point. Okay, the integration variable for any definite integral is actually a dummy variable. I said the dummy variable. I will tell you the meaning. Okay. Now, for instance, if I want you to evaluate, now let's say two integrals. One integral is the integral, so now let's say from 0 to 1. One integral is x squared, and then dx. Okay, we have seen the answer to that many times. Okay, if you want me to use FTC to evaluate the integral, you know the answer is going to be 1/3. Okay, so the answer is computed using, you'll find a particular antiderivative of the integrand. You have x cubed over 3, and then you evaluate the antiderivative from 0 to 1, right? You know the answer is 1/3. I think you did many questions like that. you know the meaning. Okay. Alternatively, I'm trying to show you why I call the integration variable the dummy variable. Alternatively, if I want you to evaluate the integral, so now let's say from 0 to 1, if I replace, I mean from 0 to 1, okay. If I replace the integration variable with t, if I want you to compute t squared and then dt, you're going to do the same thing, right? To evaluate that integral of t, you get a particular antiderivative of t squared, so which is t cubed over 3. And then you evaluate the definite, you evaluate the antiderivative from 0 to 1. You still have 1/3. Okay. Why did I call the integration variable the dummy variable? A dummy variable? That's because the choice of the notation of the variable, it doesn't matter. I'm trying to say this integral of x is the same as that integral of t. You can safely replace this x squared with t squared, and then replace dx with dt. Okay. I'm trying to say we say the integration variable a dummy variable because it's independent on the choice of the notation of the variable. Okay, so that's my point. Okay. That's my point. So did I, any questions about this? I think it's simple. For any integral of x, for any definite integral of x, you can always replace x with any other variable, like t, like y, like any other things, right? That's why we say the integration variable a dummy variable. Alright, after you know that, now let's try to understand the meaning of the function using a particular function. Okay, using a particular function. Now let's say f of x is equal to x squared. Okay. This g of x, some people say g of x, the upper limit function. Now let's try to use a particular function to understand the meaning of the upper limit function. Okay, I will show you in both ways. We'll try to evaluate the integral. Okay, I know it's not quite reasonable to use FTC to tell you the meaning of FTC, but I will show you the meaning of the function. Okay. If the integrand is x squared, and then the if I want the function, so now let's try to compute g of x. Okay, g of x. So temporarily we fix a, we fix the lower limit of a. So can I replace a with 0? So to make the thing simpler. Okay. I'm going to replace to fix the lower limit. I'm going to simplify. I'm going to use 0 to denote the lower limit. Okay. Now g of x is defined as a function of x. The function of x is defined using the integral from 0 to x, and then you evaluate f of t if the function f of x is x squared. So because the integration variable is a dummy variable, the integrand, I can replace the integrand with the t, right? And then we compute f of t and then dt, right? In this particular case, the integral now is evaluated from 0 to x. When evaluating the integral, you temporarily treat x as a constant. Okay, and then you integrate. You compute the integral for the integration variable of t, and then after you get the answer, you treat g of x as a function, in particular you treat x as a variable. I will make my point. Okay. F of t, the function again, f of x is x squared, so f of t is actually t squared. Dt, right? You do the same thing. To evaluate the integral, we kind of use ftc to evaluate the integral. Actually, it's possible to use the definition, the limit of the Riemann sum to evaluate the integral. But in order it's easier to have the answer, I'm going to use ftc to compute the integral. My point is to show you the meaning of g of x, the meaning of the upper limit function. Okay. You get a particular antiderivative of the integrand, which is t cubed over 3, right? And then you evaluate the antiderivative from t value of 0 to t value of x. So do you see you have t cubed over 3? Actually, you have x cubed over 3. Okay. You have x cubed over 3. Again, after you get the answer to the integral, you treat x as a variable to mean the value of g of x is dependent on x. For each value of x, you have a value of g. Now, for instance, the function is a rule anyway. To define the rule, all we need is to know how to evaluate the function at different numbers, right? So now let's say if I wanted to compute g of 0, you look at the meaning of the function. Okay, g of 0, you replace x with 0, you have 0 cubed over 3. So the value of the function g at 0 is equal to 0, right? If I want you to compute the g of 1, all we need is to replace x value with 1, so you have 1 cubed over 3. So the answer is 1/3. Okay. If I want you to compute, so now let's say the value of the function g at 3, you are going to get the answer to a question on the assignment. So because the function is defined by the variable, the location of the variable is at the location of the upper limit. So that's why we call it upper limit function. Okay. That's why I said it's possible to use the definition to evaluate the function g. Okay. So g of 3 is computed using, you replace the upper limit with 3. Okay. Or you could use the function. You replace x value of 3. I think you have 27 over 3. So which is 9. Right. That's the answer to the second question regarding the definite integral, using the definition to evaluate the definite integral. Okay. I was trying to say if x value of 1, it becomes the first question on the assignment. I mean the question regarding using the definition to evaluate the definite integral. Okay. If x value is 3, you have your second question. So, I will also show you. Any questions about this? I'm trying to say, all I'm trying to say now is the upper limit g of x, if defined that way, it defines a function of x. Okay. The function of x is defined using an integral from 0 to x. Okay. I will also show you the meaning using the geometric meaning of the definite integral. Now let's recall the geometric meaning of the definite integrals. Okay. In this particular case, the function is x squared. F of x is x squared, and upper limit function, we kind of fix the lower limit. The lower limit is 0. And then we change the upper limit. The upper limit x is the variable, right? And then you look at the definition again. The value of the function g at any value of x is defined as the integral from 0 to x. Geometrically, the value of the function g at any x value. You look at the mouse cursor. Now let's say that's x value. The value of the function g at any x value is defined as the area under the graph of x squared from 0 to x. The variable is the upper limit. The red dot. Okay. This value can be changed. So now let's say if x value is, I was using b, so because decimal, so decimals does not let me to use x for the upper limit. I'm trying to say if you replace the upper limit with 1, the value of the function, of the function g of x when x value is 1 is given by the integral from 0 to 1. This number is 1/3. So we have seen that, right? And likewise, if you replace the upper limit value with so now let's say 3, you have the value of the upper limit function, so which is 9. So we have seen that already. Okay. Now I want you to see the meaning of the function, so geometrically. Okay. The value of the function g at x value of 3 is, so geometrically, is the area under the graph of the function x squared when x is from 0 to 3. You kind of change the upper limit, right? For each value of the upper limit, you have a number corresponding to the value of the upper limit. So the meaning of this number is the area under the graph when x is from 0 to x. Okay. That defines a function. This is the upper limit function. All right. Actually, I was trying to use a simple function to show the meaning of the upper limit function, but the integrand f of t or f of x can be very complicated. Okay. But in any case, I'm going to show you the meaning of part 1 of FTC. I will show you the meaning of part 1 of FTC. Okay. I told you the meaning of g of x. Again, it's called the upper limit function. So not many people are using that name, but it's a proper name. Okay. This function is the upper limit function. I forgot to mention the condition, so do not forget the condition is that the function f of x, we can treat the function f of t, so must be continuous on the interval from 0 to b, from a to b, okay, in general. This will ensure the limit of the Riemann sum, or the definition of the definite integral from 0 to x is defined. Okay. Now again, part 1 of FTC is that it's always true that the derivative of the upper limit function is f of x. I want to repeat, it's always true that the derivative of the upper limit function is f of x. You can see it from here. If the function, the integrand, is x squared, or in this particular case, you could write the integrand as t squared dt. It doesn't matter. I told you it's the dummy variable. Okay. You have seen the upper limit function in this particular case is x cubed over 3, right? Is it true that if you differentiate, so now let's say g of x, that's the derivative of the upper limit function. The derivative of the upper limit function. Now let's verify part 1 of FTC. Okay. Now all you need is to differentiate x cubed over 3, right? Differentiate that function. So do you have x squared? You differentiate 1/3 and times x cubed. So the derivative of g of x is x squared. It means to get the derivative of the upper limit function, all we need is to use the integrand. It's essentially the integrand, but the upper limit function is a function of x. In order to get the derivative, you need to replace t with x. Okay. It's here, right? The derivative of the upper limit function is the integrand. But for these two functions, you use the same variable. So that makes sense. That's part one of FTC. I just told you the meaning of part one of FTC. Okay. Now let's work on these questions one by one. Okay. Now for question one, in the questions we are going to compute the derivative of each of the following functions. You just remember when the upper limit is the independent variable, and then the derivative of the upper limit function is given by the integrand. All you need is to replace the integrand t with x. Okay. Now for question one, it's straightforward. Okay. For this type of the questions, we prefer to use the Leibniz notation. You are going to see y very shortly. Okay. The derivative of y with respect to x with respect to x. Okay. In order to use FTC, all you need is to check is the upper limit the independent variable. So by that I mean, am I trying to evaluate the derivative of the upper limit function y with respect to the upper limit? If that's the case, all you need is to get the integrand is the derivative of the function. Okay, the integrand is t squared. You do not use t squared. This function is essentially a function of x because the value is dependent on the upper limit. Okay, you use the integrand. You write the answer in terms of t. Okay, in terms of a function of x. I'm trying to say the derivative of the function y with respect to x is not t squared. You write x squared. This function is coming from the integrand, but do not use t for the variable. Use x as the statement of the fundamental theorem, right? You look at here, the derivative of the upper limit function is the integrand, but you replace t with the x with the notation on the upper limit. Straightforward, simple, right? We just use FTC. I mean part one of FTC. So directly, it's simple. Okay. Any questions about this? I want to repeat, the only thing you have to check is, are we differentiating the function with respect to the upper limit? If that's the case, then the derivative of the upper limit function is the integrand. Okay. Replace t with x. Now we look at question 2. Question 2 is different. Okay, you see the integrand is way more complicated. Okay, I'm trying to say it's not possible to get the upper limit function in terms of an elementary function of x. It can be proved. Okay, but still, if the function the function y is defined that way, it's still possible to evaluate the derivative of the function using FTC. Okay, I will show you what's going on. Okay, now try to think, is it okay to use part one of FTC so directly? I'm trying to say, are we differentiating the function y with respect to the upper limit? We're differentiating the function with respect to x, but the upper limit is sine of x. Okay, so it's not possible to. So we are not differentiating the function with respect to the upper limit. Now let me show you what's going on. Okay. In this particular case, the rule of thumb is whenever you see the upper limit is not x, it's a function of x. I want to repeat. Whenever you see the upper limit is not x, but the upper limit is a function of x, we have to use chain rule. Okay. So y can be treated as the composite of two functions. Okay. Now now let me show you how. Now for question 2, okay, we introduce an intermediate variable u, so we let the u be sine of x. Now try to follow me, okay. Be sine of x, and then we treat the given function y as the composite of two functions, okay. And then the given function y can be treated as the given function y. Now let me copy the given function, okay, from 1 to sine of x. I want you to know y as a function of x, okay. The integrand is e to the power of t squared dt. The given function y is the composite of two functions, okay. I will write more wordings so to make the thing clear, okay. The given function y is the composite of two functions. One function is y as a function of u equals the integral from 1 to u. You see sine of x is u, right? Y as a function of u is the integral from 1 to u. The integrand is the same, e to the power of t squared, and then dt, right? That's y as a function of u. And also u is a function of x. U as a function of x is sine of x. Now listen to me carefully. I'm going to repeat, okay? The given function in question 2 is the composite of two functions if we replace u with sine of x, okay? The given function is the composite of two functions. One function is y as a function of u is the integral of the integrand from 1 to u, okay? And the u is a function of x as u is sine of x. So now let's recall the chain rule, okay? The original form of the chain rule, okay? Now in the question we are trying to compute the derivative of y with respect to x. Using the chain rule, you compute the derivative of y with respect to u first, right? And then times the derivative of u with respect to x. That's the original form of the chain rule. I mean the chain rule using the Leibniz notation. Okay, now you look at y as a function of u. Y as a function of u is defined the integral of the integrand from 1 to u. So this time the upper limit is a function of u. When talking about that function, we treat u as the independent variable. To compute dy over du, we are differentiating the function with respect to the upper limit, right? If that's the case, we use FTC. I mean, we use part 1 of FTC for this function, okay? This is, anybody want to tell me dy over du using FTC? Yeah, it's e to the power of, it's essentially the integrand as a function of u, okay? It's e to the power of, you do not write t squared, you write u squared, okay? And then du over dx, the derivative of u with respect to x is the derivative of sine of x, so it is cos of x, right? That's not the final answer yet. The given function is a function of x. To compute dy over dx, we are trying to differentiate y with respect to x. Now the final answer is equal to e to the power of u is sine of x. The final answer should be written as a function of x, e to the power of sine of x, the whole thing squared. So I write squared here, and then times cos of x. That is the final answer. Actually, the key to do question 2 is to treat the given function y as the composite of two functions. Okay, you replace the upper limit with a new variable u. Okay, so that you can treat the given function as the composite of two functions. When differentiating dy over du, you can directly use FTC. I mean part 1 of FTC. Okay. Any questions about this? Now look at question 3. So how about the lower limit and upper limit are both functions of x? Okay. Now all we need is to use a fixed number to rewrite the integral as the sum of two integrals. Okay. Now the solution. The given function y. Now let's recall we have mentioned one property before, right? If I write the property, probably you have used the property for the assignment. In the assignment question, you have the absolute value of x involved in an integral. Remember that? In that integral, you need to rewrite the integral as the sum of two integrals. We use the same trick. Okay. We rewrite the function y, the given function y, as the sum of two functions. Okay. I mean, we rewrite the function y in terms of the sum of two integrals. One integral is from x squared to 0. The same integrand, e to the power of t squared, okay, dt, and then plus the second integral is from 0 to sine of x, and e to the power of t squared, and then dt. We mentioned the property before, right? You just use any constant. You kind of imagine the constant is in between x squared and sine of x. But the constant can be any number you choose. It does not, I'm trying to say, the number you choose does not have to be between x squared and sine of x. This property is always true for any constant. Okay. We just use 0. So that the whole thing will look nicer. The same thing. Eventually, I'm trying to say if you use 1 to separate the two integrals, you can get the same answer. The same thing. Okay. If you use that property, the given function y can be written as the sum of two functions. Each of the two functions is a function of x. Okay. So I'm going to use y1 to denote the first function. So maybe from x squared to 0, e to the power of t squared, and then dt. And I'm going to use y2 to denote the second integral. So which is y2 is also a function of x. It's defined from 0 to sine of x. I mean from 0 to sine of x. The integrand is the same, e to the power of t squared and then dt. Okay. So to see y2, to differentiate y2, we have seen the answer already. If you look at question 2, the derivative of y2 with respect to x, we have computed that in the other question, right? Where is it? It's here. I'm going to copy it down. Okay, you just replace y with y2. Okay. We have seen that the derivative of y2 with respect to x is equal to e to the power of sine of x squared and then times cos of x. We'll see if I can remove this part. Again, the notation here is the derivative of y2, so that function with respect to x is e to the power of sine of x the whole thing squared. I think I removed too many things. We have seen that already. Okay. Now all we need is to differentiate the first term. Okay. Now for y1 is defined as that. Again, to use FTC, to use the first part of FTC, the lower limit has to be fixed, and then you differentiate with respect to the upper limit. Now the lower limit is x squared. For this one, you have to do two things. The first thing you do is to convert the integral. You have to switch the lower limit and upper limit. Okay. You make the lower limit the constant and the x squared as the upper limit. The integrand is the same thing. Okay. So e to the power of t squared and then dt. Right. Again, I want to use FTC. FTC has a requirement. The lower limit has to be a constant. Okay. Now, okay. That's why I make the lower limit the constant. Okay. At this point, in order it's easier to see what's going on, so can I use y3 to denote a function of x? So define as the following. Now let y3 be the integral from 0 to x squared, and then the integrand is t squared, e to the power of t squared. Okay, and then dt. And then I think you know what's going on. You know what to do now. Okay. And then for this y3, we're going to introduce an intermediate variable again. We treat y3 as the composite of two functions. So maybe for the better wording, I'm going to also to write 4. Okay, for that function. We let, so maybe I do not want to use u again. So can I use v to denote the function x squared? And then y3 as a function of u is defined as, so now let's say from 0 to u, e to the power of t squared, and then dt, right? And also v as a function of x is x squared. So using the chain rule now, okay, we use the chain rule now. The derivative of y3 with respect to x is the derivative of y3 with respect to u, and with respect to v. Okay. And then times the derivative of v with respect to x. To differentiate y3 with respect to v, now we can use FTC, right? You see the lower limit is a constant. We're differentiating with respect to the upper limit. It's the upper limit function. Okay. I mean, the derivative of y3 with respect to v now is e to the power of v squared. And then times the derivative of v with respect to x is 2x, right? We need to write the final answer as a function of x. So this one is e to the power of v as x squared, is that right? X squared and then squared. And then times 2x. Of course, you could simplify to e to the power of x to the power 4. We call the property of exponent. And then times 2x. Any questions about this? Now we combine all the results we have seen. Originally, we wanted to evaluate the function. We wanted to compute the derivative of y with respect to x. Eventually, I will write the final answer. Okay, so therefore, the derivative of the original function y, we are looking for the derivative of y with respect to x equals, okay, the derivative of y1 with respect to x. It's kind of, so negative of that is equal to negative e to the power of x to the power 4 and then times 2x, and then plus the derivative of y2 with respect to x, which is that. Okay, let's copy from here. Before we talk about how to understand the fundamental theorem of calculus using displacement and velocity, we need the physical significance of definite integrals. Suppose we are given the velocity function of a moving object over a time interval from a to b. We assume the velocity function is continuous on the time interval. We want to show the displacement over the time interval equals the definite integral of the velocity function on the time interval. Step 1. We divide the time interval from a to b into n subintervals of equal width. We use t0, t1, t2 up to tn to denote the partition points. I want to mention the two endpoints A and B are included in the partition points. T0 is A and Tn is B. The width of the subintervals is denoted using delta t. Step 2. In this step, we'll approximate the displacement over the time interval from A to B by the sum of approximations of displacements over the subtime intervals. The displacement over the time interval from A to B is evidently the sum of the displacements over the subtime intervals. If n is large, then the width of the subintervals are tiny. Since the velocity function is continuous, on each tiny subinterval, the velocity over each tiny subinterval does not change much. So we can use a constant velocity to approximate the velocity over each tiny subtime interval. We can use the velocity at any instance as the constant velocity. It's denoted by ftI star. So the displacement over the tiny subtime interval is approximated by the constant velocity f of ti star times delta t, the time elapsed. Hence, the displacement over the time interval from A to B is the total of all such approximations. It's a Riemann sum. So we can see the larger the value of n, the better the approximation. So the exact value can be computed using the limit of the Riemann sum as n approaches infinity, which is the definite integral of the velocity function from a to b. Now we are ready to interpret the fundamental theorem of calculus using displacement and velocity. For part 1, if we interpret f of t as the velocity function, then g of x is defined as the definite integral of the velocity function f of t from a to x. So we can treat g of x as a displacement function. Of course, the derivative of the displacement function is equal to the velocity function. That's the interpretation of part 1. For part 2, we also treat the integrand as the velocity function. If big F is an antiderivative of small f, then big F can be treated as a displacement function. Now, in the equation, the left-hand side is the displacement over the time interval from a to b. The right-hand side is the displacement at time b minus the displacement at time a. Of course, the difference is the displacement over the time interval from a to b. So the two sides of the equation represent the same quantity. This is how we interpret part 2.